No, slides are fine. You just maximize it if you don't have any problem.
Yeah, okay. I'll do this.
Fine, yeah.
Now you can see it, right? So now you see the full screen? Sorry.
Yeah, it's full screen. Not an issue.
Okay.
Absolutely fine.
Okay.
Yeah.
I'm so sorry.
Let me check. No,
uh,
no, it happens. Not an issue. Let me check
yeah.
streaming हो रहा है कि नहीं.
हाँ.
अंकुश स्ट्रीमिंग अभी नहीं हो रहा है स्टार्ट. देख लो ना भाई एक बार. हाँ स्टार्ट हो गया.
Okay.
Fine. So again, a very warm welcome to everyone. This is Saurav Singh from CGEC second year electronics. So here I am to host a bit this session, and the rest we have our speaker, Mr. Deepankar Sharmah, with us, and he's from University of Basel, Switzerland, pursuing his PhD from there. And we are very much we find us fortunate enough to have him as a speaker. He'll be talking about quantum computation and giving us very unique insights about what exactly and how exactly it is going to reflect in our near future technologies. So I believe it is a very important session for all of you. And do remember that we will be providing certificates for this for attending this session. So make sure you attend it to the fullest. Otherwise, we are not responsible for the non-availability of certificates for your end. Okay. So I believe everything is clear. And now I would request our speaker, special guest, Mr. Deepankar Sharmah, further and with his introduction, warm introduction. Thank you very much. A very warm welcome, sir. Thank you. Please go ahead.
Thank you, Saurav. Thank you so much for inviting me and and asking the participants to stay till the end. Okay, so yeah, let's. I'm Depankar Sharmah. I will start my presentation. As you can see my screen today, I'm going to talk about quantum computers and how it's the future of computing. I'll try to present in a not very technical details, although you are all engineers, but this particular session I just kept it simple so that it gives an overview of the concept. So let me just get my laser pointer. Yeah. So before starting, I would like to tell you something about myself. I am doing PhD in quantum and nanoelectronics lab in the Department of Physics, University of Basel in Switzerland. And I did my master's and bachelor's from ISER Kolkata in Kalyani. I hope all of you might have heard about it, Indian Institute of Science Education and Research. I was there for 5 years and I did my master's. And after that, I came to here in Basel, Switzerland. So I thought before I begin the actual session today about quantum computers, I'd just like to introduce you to Basel. So Basel is a small city here in Switzerland. It's 1 hour from Zurich and also Bern, which is the capital of Switzerland. It's actually at the border of Switzerland, which is towards Germany and France. It's very nearby to Germany and France. You can just reach in bicycle in 15-20 minutes. So, and as you can see, this is a nice picture of Basel. There's a beautiful river called Rhine, which flows through the city, and it divides the city into 2 parts. This is called Klein Basel, which means a small Basel, and the other side is called Gross Basel. This is called Big Basel. So Klein means small. Here it's a German-speaking part of Switzerland. In Switzerland, there are 4 different languages which they speak: German, Italian, French, and Romansh. And Basel is a German-speaking part. So this is the beautiful Rhine River which flows through the city, and the university is basically spread throughout this city. It's not very big. It's a small and beautiful, nice place full of art and culture in Switzerland. So if you go around, you'll see all the tram lines all over the city, and also bicycle lanes throughout the city. So it's also a cycling city. Where you can go anywhere with your bicycle. Yeah, and currently it's autumn here, so it looks beautiful. As you can see in the picture, there's the trees are all yellow and green. So leaves falling on the floor. So it's beautiful right now. This is how it looks. I got these pictures from one of my friend here in Basel. So let's get back to our topic, which is, you can see it's written, the name of topic is on the right here. Now this means quantum computer, the future of computing, the topic which is for the day. This is what it is, but it is written in binary. So all of us, all of you are engineers, maybe some are computer science, electrical, mechanical. So all of us know that computer interprets everything in the form of 0 and 1. These are called bits, binary bits. So this is what I have tried to see. So now I'll take you through the journey of how computers evolved throughout the history. Um, in early 1930s, we had computers, huge computers. Even before that, there was abacus, which was just used to do basic subtraction and addition. But the real, let's say, programmable computer was first started in 1930s, where they had a first computer which could be programmed to do basic calculations. And over the years in 1940s, we had, during the World War II, Germans and British, they developed. I don't know if you have seen this movie called Imitation Game. There, how you see the machine, Enigma machine, and then there's Alan Turing who's trying to, decode the Enigma machine. So Alan Turing, you might have learned about Turing machine in your first year of BTech, I believe so. The Turing machine, also Alan Turing, is called the father of modern computers. And then slowly there was more compact and concised computers. In 1950s, then started computers with ICs, integrated circuits, where we use transistors. So it was like a revolution in computation when you started using transistors. So if you all know transistor is basically, it's a switch. If it's 0, it's a switch off. If it's switch on, then it's 1. So it's off and on. That's a 0 and 1, and that's how the computer processes all the information. Then in 1960s, there was more compact and you could do more with the computer. Then finally in 1970s, there was the first tabletop computer by this company, which was the predecessor before Apple. This company, along with Apple, they prepared this computer which you could put on top of the table and then use it. Then finally in 1984-85, we had the first Macintosh by Steve Jobs from Apple. So this marks the first personal computer. He first made the personal computers which was available for everybody to use. And in 1990s, it was more customizable, according to, you could change how much storage you want, what all things you want to attach to it. And then it was more compact, the monitor and keyboard and more concise and compact. And in 2010s, we have touchscreen computers, laptops. And even if you go now, you see we have tablets and mobile phone, which is itself a huge computer. It does much more than what they used to do with a huge computer which used to occupy the whole building in 1950s. And even now they have smart watch, and everything, the whole thing which a computer can do is stored inside the watch. But what's next? That's a big question. What's coming next? What's the future? Why do we ask this question? Because we all know Moore's law. Moore was a scientist who gave his law that every 1 or 1.5 year, the number of transistors we use in a chip doubles. And that means the size of the transistor gets halved every 18 months. And this trend has been seen that from 1950s, every 18 months, the size of the transistor gets half. So now we are at the time when the size of the transistor is at the order of nanometers, like maybe 10 nanometers, 7 nanometers. So what next? Maybe we say we go to angstrom, less than nanometer. But the problem is the size of an atom is in angstrom. So you cannot have a transistor which is smaller than an atom. because now once you go to the size of an atom, then there are quantum phenomena. There is the atom is no more a particle; it behaves like wave or particle. So there's all quantum mechanics coming into play. So now comes the real issue, because you cannot go further below. The transistor cannot become much more smaller. So there comes the idea of using some different form of computation. And you might all know this guy. He is Richard Feynman, one of the brilliant physicists of 20th century. And he gave this idea. He said that if you want to simulate nature, if you want to understand nature, then you have to do it in quantum mechanically, because the nature is quantum, it's not classical. So if you want to understand, if you want to simulate something in nature, you have to make quantum computer. And it all started by a conference which was happened in 1981, which was organized by IBM and MIT. And in this conference, this big scientists of the time, they got together, scientists and engineers like all of us. They got together, and then it started the idea of having quantum mechanical computation, quantum computing. And then after that, for many years, they developed algorithms, because initially the hardware to make a quantum computer was very difficult. So for few decades, a couple of decades, they started making algorithms like Shor's algorithm, which is used to factorize. So factorization is a hard problem. If I say what is 5 cross 3, it's 15. It's easy problem, multiplication. But if I ask what is 15, prime factor of 15, then it's a hard problem. 5 cross 3. For small number, it's easy. But if I ask you what's the prime factors of 4, 5, 9, 3, 6 to 1, then it's very difficult to say. But if I give you big two numbers, then you can multiply and get the bigger number. So they're called NP hard problem, non-polynomial time problem. And quantum computer can solve this problem. So if you're aware of this, the RSA, which is how the whole security system is based on right now, your email, your bank account, everything is based on prime factorization. So because it's difficult to crack. Now, let us go and understand what is a quantum computer, and how can we use some of these properties to build one quantum computer. So as I told you, as you also know, that computer takes everything in bits, 0 and 1. So for a quantum computer, you need something called quantum bits, or in short form is called qubits. Now for classical bit and quantum bit, there are two things. So let's say classical bit, it can be either 0 or 1. So if you have 2 bits, then the state could be 0, 0, 0, 1, 1, 0, or 1, 1, right? But contrary to this, if you have a quantum bit, it can be, if you have a single quantum bit, it can be in 0, it can be in 1, or it can be in a superposition of 0 and 1. That's the whole amazing thing about quantum physics, is that the wave function can be in a superposed state. So now if you have 2 qubit system, then you can have a combination of all of these 4 states, as you can see here. And then alpha, beta, gamma, delta are all real numbers. So now you can change this real number, and you can get infinite number of states using these 2 qubits. So therefore, I won't go into much detail of what this sphere is. It's called block sphere, and all the points in the sphere represent different states. But the idea is, I'll talk about superposition later, but the idea is that 2 qubit can, or even a single 1 qubit can have different infinite number of possible states. So for example, therefore, what comes here is that we can see in terms of memory, if you have a 1 qubit, then it can be 0 or 1, both. But in bits, you need 2 bits for that, which is equal to, if you say RAM, random access memory, it's 2. So similarly, if you go on increasing the bits for, as you all know, 1024 bits is equal to 8 bits is 1 byte, right? So 1024 bits is 128 byte. 8000 bits is 1 kilobyte. So 1 KB of data needs 8000 bits, more than 8000 bits. But if you have qubits, then it only need 13 qubits. So this is remarkable. In place of 8000 bits, 8000 transistor, you can just use 13 quantum bits, which is huge. And if you go even further higher, you see for 1 GB, to store 1 GB of memory, you need 8 billion bits. Whereas if you have qubits, you only need 33 qubits. So that's, quantum computer is much more helpful when you go to higher number, higher computation. For smaller computation, it's not that useful because it's similar as classical. But if you increase the numbers, then you see remarkable achievement here. 33 qubits is equivalent to 1 GB of, it can store 1 GB of information in 33 qubits ideally. So if you have a nicely running quantum computer. Similarly, you can see if you have a 63 qubits, you can store like all the information in the universe within itself, just in maybe 100, 200 qubits. So that's the remarkable idea behind quantum computation. Now, what makes quantum computation possible? What is this quantum phenomena which makes this possible is superposition and entanglement. So these are two beautiful phenomena in quantum physics. If you have taken any quantum physics 1 course, you would know about it. What is superposition? Superposition is the ability to have multiple states at the same time. Like if you have a classical bit, as I also told before, you have a state pink and a state green, but in a qubit, the pink and green can remain in the same state, superposed together. And entanglement is when two particles are connected, are correlated to each other, and they share some information within themselves, and changing one state of one particle changes the state of the entangled particle. And also important is that the third particle cannot have information which is shared in between two. So these two phenomena, superposition and entanglement, this makes quantum computation remarkable and possible. Yes. So I'll just show a short video here. As you can see, the classical bits, if you want to solve this maze, if you want to get out of this maze, you enter through one entry point and come out through other point. Then if you use a classical bit, what you have to do, you can watch it again. You start with 1 and then it gets stuck. Then you start another computation round, you start, and then it gets stuck. Then you start with third computation round, and then also it gets stuck. And then you start with fourth, and then you get out of the maze. But if you look at the right hand side of the figure of this screen, I'll show you again. You see, once it enters and it sees there are two possibilities, then it splits into two, and then it continues. So in a classical computation, you have to do 4 iterations in this situation. But whereas if you have a qubit quantum computation, you can come out of the maze in a single iteration, in just one go. And this is possible due to superposition. So if you say that the path which comes out is blue and which gets stuck is orange, since the qubit has information of blue and orange at the same time, it has both the states together, so it finds its way. So therefore, since there are only 4 steps, but just imagine there are like 2000 different possible paths in a maze, then it becomes very important, because quantum computer can come out of it in just 1 iteration, whereas classical computer, let's say in worst case scenario, takes 2000 different steps. So therefore, quantum computation is said to be exponentially faster than classical computation. Therefore, in doing huge calculations, this is where the quantum computer comes into picture. So where will it be used? What will you do with quantum computation? We will do quantum simulations because the nature is quantum. So you cannot do classical simulation. Whenever you do any simulation, it should be quantum. Then there's cryptography. Cryptography is the security. All the problems, all the security problems can be solved using quantum computer, because then it would be highly secured. No one, although the prime factorization, which is the basis of all secured process right now, all security services, although it's very difficult, but every time they have to change the number. I mean, someone can use supercomputer for 20 years, and then maybe they'll be able to factorize the problem, and then get a, I mean, you have, how security works. You have a public key, then you have a private key, and all those things. So if you have quantum cryptography, quantum key, there's a field called quantum key distribution, then you'll have very secured communication, because in quantum mechanics, when there is no eavesdropping. I mean, if you share if parties share some information, third party cannot come and eavesdrop in between. There's a beautiful theorem in quantum computation called no cloning theorem. You cannot clone it. So there are search algorithms. There is a Grover search algorithm, which is exponentially faster than classical search algorithm. There is factorization problem, which I discussed about. There's source algorithm, which is the algorithm for factorizing in big numbers. So for prime factorization, when I say factorization, I mean prime factorization, because that's a hard problem. And there are optimization problems, which I will show a few examples later, and also quantum machine learning. Now, just to give you an example, let's say there's a table and there are two people who needs to sit on the table. Then how many ways can we make them sit? So it's a basic combination problem. It's 2 factorial, right? It's 2 ways. There are 2 ways in which 2 people can sit. Either you sit the other way and I sit this side, or I sit the other side and you sit this side. So there are 2 ways. But now if I increase, let's say there are 5 people who need to sit in this table, then there are 120 different ways to do this, to find out the different arrangements. So, but now if I say there are 10 people, then the number of ways becomes highly very big. It's almost 3 billion, more than 3 billion different ways, 10 factorial, to make these people sit around. So now if you have 100 people, let's say, then it would be 100 factorial, and this would be a huge number. When to solve this problem would take ages, whereas if you have a quantum computer, you can do it in a matter of seconds. Other examples, like for companies, it's very useful in companies. You have logistic company, you need to deliver some goods to 50 different cities. You have 50 different routes, and then you want to find out an optimal route so that you can save your cost on fuel and other things. And here comes the use of this highly exponential fast computing, which is not very easy to do using a normal computer. Then you might all know about trading. When you trade, then you do the analysis of your risk analysis. So in all of this analysis, there are so many possibilities that could happen, and in order to optimize this, it's very difficult. Therefore, it's like gambling right now. So if you've invested in cryptocurrencies, bitcoins, ethereum, or if you are doing stock marketing, then it's very, you never know. Today you invest something, and it's like tomorrow you're not sure whether you're going to go up or down. But if you have a quantum computer, you can simulate all the possibilities and find an optimal solution out of this. And the most important of all of this is in pharmaceutical companies. So what quantum computer can do is, if you have a quantum computer, so for example, the caffeine molecule, it has 160 different parameters. So in order to simulate quantum mechanically, you will need 160 qubits. But if you want to simulate it in a classical computer, it needs 2 to the power 160, which is more than the total number of atoms in the whole universe. So it's difficult to simulate molecules in a classical computer. But if you have a quantum computer, then you don't need chemistry labs anymore, because the reaction which you do, which you do in a test tube, you put some water molecule, you put some acetone and IPA or ethanol. This whole thing which you do in a test tube can be done inside a computer, which is not possible right now. So for those who are working in manufacturing new drugs and new medicines, they don't have to do all these things in a laboratory where there are so many parameters and factors which are not sometimes there are other factors which doesn't lead it to success. So therefore you can do everything inside a computer, and it would be very easy to understand how these drugs or molecules are interacting with each other, and then you can make new drugs, new molecules, new medicines. So it's a very it is one of the most visionary idea which quantum computer has behind its development. Now also there are different kind of things you could do. You could make like actual quantum computers and do solve problems. You can also work on simulations. You could also work on developing quantum softwares. They're also used for communication, quantum communication, like cryptography and others. You can also use for meteorology and sensors. So there are different things you can do in quantum computing field. In this particular session, I'll be talking about quantum hardwares, like proper quantum computers, how to make them. So right now, as you know, what the computers we saw in 1950s were like huge, need a lot of room because there were so many constraints. Similarly, quantum computer nowadays are in those phases, in the initial phases where you need huge big machines. I'll show you in a bit. And so there are different quantum technologies people are using. So what the ultimate idea is, they're trying to make qubits. So how can you make qubits? You need something, you need to exploit the quantum mechanical phenomena, and this is possible only when you go in the level of an atom. So one possibility is like you use the charge, positive, negative. Positive charge is 1, negative charge is 0. Or you use the spin of an electron, up spin is 1, down spin is 0. Or you use some other things, cold atoms or ions. So there are so many other technologies, so many different technologies, right? There are superconducting qubits. So superconducting qubits are made up of Josephson junctions and other things. We don't go into details. There are quantum dots. Quantum dots. This is particularly where I work. I myself work in using quantum dots, the spin of an electron. So in quantum dots, what you do is you isolate a single electron and then use the spin of the electron as qubit. So if it's up, we say it's 1, and if it's down, we say 0, and then we have like classical 1, 0. Here we have qubit with 1, 0, and also 1 plus 0 by root 2, and all other possible states. Also, there is other technology which is NV centers, which is called nitrogen vacancy center in diamonds. So naturally occurring diamond, they have a defect, and in this defect, there are some electrons present, and now we exploit this defect and use this electron which is trapped in this defect as a qubit. They're also promising because I would tell you later that all other technologies, they need extremely low temperature to work, because we don't want any noise to interfere or disturb the coherence of the state. So if there is any noise from environment, then the information is lost and we cannot proceed. So all the quantum computation technology, everything is performed at a temperature of almost 0 Kelvin. So which is minus 272 is 1 Kelvin. But even everything is performed at a almost 0, like 10 millikelvin, 20 millikelvin. So we do all our experiments at around 16 millikelvin. So it's like extremely low temperature. So you need big machines, shield, vacuum sealed, because everything goes inside the vacuum. then you have to take it down to millikelvin by using liquid helium. Liquid helium is usually at 4 Kelvin, 4.2 Kelvin. Then you use mixture of helium to go even further to 1.5 Kelvin, and then you use dilution technique to go even further to a few millikelvins. Then there are also neutral atoms, laser cooling, for example. By laser cooling the atoms, you can use them for computation. Then you have ion trapping an ion into these fields by using electric and magnetic field. Then there are resonators, topological qubits, carbon nanotubes. There are so many different technologies out there. Everyone is trying to see which are the best qubits. And because qubits need to be stable. If you have qubit 0, 1, but you just lose information in very short time, then it won't work. So first requirement is you need to have stable qubit, and second requirement is you need to scale up. Only having qubit is not sufficient. You need to be able to scale up, because we need, at some point we need to have thousands and millions of qubits. So, and there are other problems like errors, because you have qubits, you don't only have qubits, you have so many other things, the environment, and there are different lines, microwaves and everything going on. I'll show you. So basically, what does this look like? What does the fridge or the machine which I'm talking looks like is like this, as you can see here. So this is the inside of the machine. Outside would be covered by this shell, like above here, everything would be covered, and then it would cool down to millikelvin level. Like there are 5 different parts in this machine. The first one is the shell, the top shell. This is like the skin of the body. And then the next is the wires which are going down, because the quantum part is only the qubits. Everything else is the regular electronics. So these are microwave lines. They're microwave coaxial cables. If someone of you are doing electronics, electrical, then you know that microwave travel in coaxial cables, waveguides. So these are called the nerves of the body. So we have skin, we have nerves, then there is the skeleton, which is the heating system. So it needs to cool down. So in order to cool down, you need to have some flow, transfer of heat, transfer of the energy. So this cools down the system, the whole system. And there are different plates here, as you can see. This is the topmost part is around 300 Kelvin. Then you have 4 Kelvin. Then you have even goes down. When you go down, it's 1 Kelvin. Then you have 500 millikelvin. And when you go ultimately down to 5 here, then you are at a temperature of a few millikelvins. So the 5th part here is called the brain of the machine, and this is the quantum processor. So this is where the qubits which we make will go inside. So the whole quantum thing, the computation thing, is happening here, where you exploit the qubit, you make changes in the qubit, and then do the computation. And all others are so basically everyone use microwave signal to input the information and also read out the information from the qubit. So these are all microwave lines going down. And yeah, so therefore the quantum processor, this guy here inside, will have qubits which are made from all of these different technologies, maybe using there are superconducting qubits, there could be quantum dots, there could be others. So I'll just give you a small idea about the spin qubits in quantum dots, because this is what I'm personally working on. So what is a quantum dot? I told you that what if you restrict, suppose you have a 2D material, planar material, you have quantum well, which it's like a sea of electron floating. Then what you do, you put in some potential barriers, and then isolate an island. You make an island which is isolated, and then slowly you either add 1 electron or you remove 1 electron. So the idea is that you can manipulate a single electron at that level. So here, as you can see, this is like a heterostructure. It could be silicon, silicon germanium heterostructure, and then due to this different band gap and band structure, we'll have electrons flowing below this thing. And now, if you use these gates are you might all know, you all are engineers. Gates are basically DC voltage. If you just apply some DC voltage, then due to the field effect, because these are called FETs, field effect transistors. So due to the field effect, then you'll have, it'll create a barrier so that the electrons from here will not be able to escape or go anywhere else. So this is like two quantum dots you can see here. This is a left quantum dot and right quantum dot. And with other manipulation techniques, you can make sure that the spin in one of the quantum dot is left spin, the other one is right spin. So there are much more technical details which we won't be getting into in this session, but this is the idea that as you can see here, you have a heterostructure, quantum well. Quantum well is like you have a sea of electron, two-dimensional electron gas, and then you apply some magnetic field, some current, some AC magnetic field, which is usually the microwave, and then you have gates, different gates. Gates are the voltage electrodes where you apply voltage, and by applying voltage, then you create such a wall, potential barrier. So now you see here, if you create a barrier like this and you trap some electrons inside, then it won't be able to escape it unless it tunnels. And even by controlling some other, changing some other parameter, you can control the tunnel rate, and you can have add or remove a single electron in the system. And for manipulation, you use some microwave, let's say. So we use microwave with a microwave photon of energy h nu, and then by you applying some microwave energy, so what happens is spin up and spin down is are two different energy levels, right? One is spin up is higher energy, spin down is lower energy. So when it's spin down, that means you are at zero state. Spin up is one state. So now to go from 0 to 1, you need to give some energy, because it goes from down spin to up spin. So you give this energy in the form of microwave signal. That's how you manipulate. So you change the state of the system. So that's how you change, you make computation. And similarly, you can have double quantum dot. Initially, we saw single quantum dot. Now we have double quantum dot. Similarly, you make two different quantum dots with three barriers and other few other gates. So that's how you can increase the number of qubits by this. Now I'll show you how these machines look like. You can see here, this is how the machine looks like. It takes up almost a room, a huge space. There is not only this thing, this is like the main thing, but other than that, you see there are so many lines. There are classical normal computers which is used to control all of this machine. There are control hardwares, there are vacuum pump, you should pump the whole chamber. So what I showed was inside, now it's covered with shield, because the inside thing needs to be pumped down to very low vacuum so that the heat is not transferred to the surrounding. So now when you open this is the computer from IBM. It's a big machine, a big company, you might know. So if you open it, there are different this is how it looks like inside of this computer. There are many microwave lines going down, or also it could be a smaller version, so bigger. So the number of lines could differ, but if you want more and more qubits, there should be more and more microwave lines going down. And this is one from Google. Google also has their quantum computer. So you might have heard at some point that these big companies, everyone is now working in quantum computing. All big companies, you name them, Amazon, Google, IBM, Alibaba, Huawei, Intel, any company, everyone, because everyone knows that this is the future. This is what we're going to have in like 20-30 years from now. Quantum computers would be ruling in terms of computing. So there are many startups also, if you are, and this is a field where everyone can contribute. Either you are a computer science student, either you are electrical engineer, or you have done electronics, or you are a physicist, or you are a mathematician, um, experimental physicist, theoretical physicist. Everyone can contribute because there are so many factors which is here. There is engineering, a lot of engineering. There are a lot of physics when you go into the brain, the quantum processor. Outside quantum processor, there's a lot of mechanical things you need to take care of. There's a lot of electronics you need to take care of. There's capacitors, inductors you need to make. So there's a huge demand right now. So if you have any idea about quantum computation, anything you want to know about it, it's very very easy to get to work, even if you are not directly from quantum or physics field. Now, for example, this is a 8 qubit. Here you can see these are qubits. You cannot see it right now, but if you, because these are like nanoscales, everything here is in a dimension of micrometer or nanometers, very small. So there are resonators and qubits, just as in junctions. We don't go into detail of what it is, but this is an 8 qubit. Here is 1 2 3 4 5 6 7 8 8 qubit superconducting quantum processor. So this is the quantum part which goes into the brain of the computer, as I showed you earlier, and the rest is normal electronics outside. So this is fabricated in ETH Zurich, and this is our computer in my lab. So this is what we have. This is our machine. So as I showed you, most of the machines right now are similar kind of machines. So there are microwave lines going down, and at the end here below, it's 16 millikelvin when you pump it, and so there is where we put our sample. This is the processor you can see in the right side. This is the processor which we have, and here is the quantum dot and the resonator, which you cannot see. If you see it clearly, maybe you can see some structure, but there's where we have nanowires, and in that nanowire we have quantum dots, and those quantum dots are manipulated by using some gates, and then there's resonator, we do readout, and everything happens here. So basically right now it's the quantum computers are the phase of development, primitive phase. Some of the companies have 100 qubits. Google says they have 50 qubits, but again there's a problem in scaling up. So with this, I would like to thank you all for your attention. If you have any questions, then you can ask me. You could reach me in my email or LinkedIn. And yeah, thank you for your attention.
Thank you. Thanks a lot for this wonderful, wonderful session. And now I would rather request our audience to, if they have any questions, feel free to ask him, and we are more than your questions are more than welcomed. Please, any one of you, either you can, if you are a shy soul, then you can put your question on the chat box. Either otherwise, we are good to answer your questions on by unmuting yourself.
Yes.
Anyways, so I have already provided the attendance link in the description in the chat box. Kindly fill that form up for your set. I have some personal questions to ask. Okay.
Okay.
Yeah. So, how do you recommend the electronics or electrical guy who is not from computer science background, to be precise, or do not have a very in-depth knowledge of computers, and how exactly computers work, the compiler design, the BD, that database management system, and these all. So, how do you recommend him to enter in such interesting and future demanding field?
Yes, so it's a very good question and very important one for everyone. So thank you for asking this. So as you see the computer here, it requires a lot of electronics. I think electronics guys have a lot of things to do in here, because even here when we make our sample, we always go to the electronics workshop and ask them to build this PCB for us. We ask them to make some capacitors, inductors, because the whole line, it has hundreds and hundreds of cables going down there. So there's a lot of task for electronics people to do. The physicist, just the last end of it, where you have to make, although it's a very important part, But the workforce, the main workforce which is required in terms of making it, producing it in large scale is, I think, we'll need a lot of engineers from electronics background for making all of this electronic system. There are coaxial cables, and you see there are attenuators, circulators, isolators, directional couplers, all of these devices which are required to use inside this computer, inside this fridge, in this machine. And even outside we have the normal computer, the interface. Then there are other control hardwares which is not shown here. There is a VNA, vector network analyzer. There are other quantum analyzers which actually are regular electronics device. So in that way, I would really recommend, if someone is interested, you could look for it. You could ask, just get internship in some of these companies, and this could be life changing, because there's high demand of engineers who would like to work in such field, and it doesn't require much knowledge about quantum physics to start, because it's not very difficult subject to start with, because there are many different scopes in this.
Okay, so let me tell you about myself. When I listen
Yeah.
about quantum physics, so I remember of H. Sharma last chapter. Okay, which I never
Okay.
read. Okay, so I think that this is people are very scary, and
True.
they means they just dream of how do I get rid of this computer, this quantum, right?
Mhm.
So this seems really tough after listening classical model and quantum model, this that, after listening
Yeah,
Sir
but you
Richard
don't
Feynman.
have
Yeah.
to. That's what I'm saying. My whole idea is you don't have to go into the quantum physics part. You can be
Okay.
just an
Okay.
engineer by yourself and just do the electronics for the machine,
Okay.
right?
Okay. Okay.
Just
So
build
here,
some capacitors, and you might make a bias T, or you might make a circuit to, how to make this microwave flow to the system. That could be the job. Yeah.
fine. So your reply is, you don't need to be an expert in quantum, right?
Be an expert in quantum physics to be a part
Fine.
of
Fine.
quantum computer, unless you
Got it.
want to develop qubits. That's a different
Okay.
issue.
Okay. Okay. Got
Yeah.
it. Got it. So an engineer may contribute in different sense, right? By his
Yes.
engineering knowledge.
Yes.
Got
Yes.
it.
Yes.
So here I have a question with from Avirup Gattat, who is one of my friend. So he
Mhm.
has to ask that, Bhaiya, you are now in foreign for PhD, which is right.
Yes.
Did you
Yes.
appear in GRE and equivalent exams? So he has to ask this.
Just a moment. I think I will just unshare my screen now. Okay. So no, yes, I'm doing my PhD in Switzerland, and I didn't appear for GRE. GRE is, I think, it's required when you go to the United States. But if you want to come to Europe, then it's not. As far as I know, it's not important. It's not required here. Maybe some of the universities, they ask for some other language exam like TOEFL or IELTS, uh, but even without those things you can come, because the only thing is like you need to know what you are doing. Look for similar kind of labs who are working in such field. Then you can talk to them, have interviews, and then they will hire you. So nowadays I think the days, the time has changed. It is no more that you need some certificate or some high grades, only 9 points, 8 points, 10 points to go abroad or do it. It's not that. It's all about how much passionate you are, because let me tell you, it's really different when you are doing masters or bachelor's, BTech, and then when you start a PhD. You have to do everything again, learn things on your own. PhD is completely different, so they don't expect you to know everything from the beginning. You just need to have that passion that you want to do. And yes, of course, the basic background is always required. So just to answer your question, that no, I didn't appear for GRE, or actually I didn't appear any exams, any equivalent exams. Like I didn't even appear for any language exams, because mostly in Europe you don't need an English exam. Because for me, I was always studying, but I mean my first language for my academics was always English. So it's, and the second question is, are you getting stipend? Yes, it's called salary in Europe. It's PhD is like a job. They pay you salary, which is sufficient for you to live. So and the salary is different in different countries. If you come to Switzerland, they pay you well, nice, because they're rich. If you go to other countries, also they pay you pretty good. So if you can, yeah, it's you don't have to bring your own money. You're everywhere, it's paid nicely for PhD, if you get a nice PhD position. Yes.
Got it. So, so my next question would be, as I have talked to many of my batchmates and classmates. So they have
Yeah.
one question inside, and no one is answer it, cannot answer. No one can't. Anyone can't answer them because we are
Okay.
not from a foreign background, or we are not belong to some. We have not interacted much with someone who has doing his studies in foreign, right? So you are a unique, if I have to say.
Okay.
So,
Yeah.
how do you recommend a BTech student studying in one of the government colleges of West Bengal, which is, I won't say bad, but not
Mhm.
comparable to IITs or NITs, to be precise and frank with you,
Yes.
right? So
Yes.
how do you recommend such a student who is passionate about some of the research topics,
Yes.
be it quantum computation as well? So how do you
Yeah.
recommend him or her to go abroad and follow his dreams or passions in terms of research work, to be precise?
Yes. 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 Saurabh. Yeah, I understand. So I think my example would be good for everyone, because I just told you that I didn't appear any of the exams which is so much of hype in India. If you just see that everyone is running after GRE, TOEFL, and everything. But I think this is not an absolute requirement. And also there is some you need to have a paper published. I didn't have a paper published. So I think most important thing is you need to have passion. It's all about communication, how you talk to people, how you present your idea. So you should be very much excited to present your idea to people. You should just write down. You should get into LinkedIn right now. You should get your profile in, make a nice profile, uh, text to, you should find out whatever you are interested in. You're interested in electronics, you just find out all of this lab who are doing research in this field, and text, send them messages in a nice way, of course, that I have done this is what I can do, these are my qualifications, I'm passionate about this. You should show them that you can do. And then you should ask them, is there anything where I could fit in with my skill sets of these many things. And then surely there would be you'll get chance. At least they would maybe call you for an interview, and that okay, you can. Then after that, it depends on whether they want what kind of people they want in their lab. But yeah, the idea is to just express yourself. You should know what it's not about what following what everyone is doing. I mean, 100 people are going and appearing for ZRE, so I would also go and do ZRE. That could be a requirement, but if you want to go to the United States, then that's an absolute requirement. So you have to do it. But other than that, you shouldn't get disappointed that okay, I couldn't make a GRE, so I cannot come and go to foreign. It's not that actually. It's just about awareness. You should be aware of what's going on in the world. You should use internet very wisely. Everything is there in the internet. You have google.com, that's it. Everything is there. Google.com, google.com, that's it. That's your friend. I mean, you can get anywhere from internet, at least in this present world in which we are. And after COVID, everything is online, so you could take courses in edx or from MIT. There are online courses which they offer for free. You could attend few courses, they give you a certificate, and after that you could, many other people, they accept these certificates. So these are some of the ways you need to figure out, be aware, and just yeah, express yourself. That's what I can say.
Okay, nice. So your point is clear about what exactly he or she need to do in near future, and proceed accordingly, right?
Yes, and you
So
should be aware of what's happening in outside world. You should know.
yeah,
That's
yeah,
called
yeah. Got it.
self-awareness. Yeah.
Got it.
Yeah.
Your awareness is the key, right? So
Yes.
here we have a super interesting question from Ankush Shah, first year, right? So he's telling that can I get admission in your university for my MTech after completing my BTech? So this deserves a
Okay.
nice answer. Yeah.
First of all, I think there's no MTech in this university because it's not an engineering institute. So, but there are other. I think for MTech, it's very rare to get a stipend or scholarship. Many people I have seen, there are people coming doing masters here, but they do on their own because they don't pay you for masters. But for a PhD, it's like a job, so they pay you well. So to answer your question, there is no MTech course in my university. So, uh, but you can maybe do masters in physics or nanoelectronics. So in my university, there is nanoelectronics, nanoscience also. Yeah.
So I believe you got your question answered, and it was really a very funny question to be precise. Yeah. However, so here we have a Rima Ghosh has a question, who is I believe my batchmate. So you have discussed various advantages of quantum computing. Can you discuss some of its disadvantages? So yeah.
Um, Disadvantages of quantum computer. So I'm thinking that means there are not many. So disadvantage, since we are at the beginning phase of quantum computers, like as I told you, in the 1950s when there were computers still coming up. So there's no disadvantage of quantum computer, but there are disadvantages in doing, the thing, because you might be doing some particular, like I'm doing quantum dots for like my whole PhD, and maybe after 5 years we find out that quantum dots are not the qubits. You have to do superconducting qubits, or you have to do NV center. So that could be a revelation after I finish my PhD, and then it could be like this. But that could be a disadvantage, but not a disadvantage of quantum computers, but the disadvantage or of the small thing inside, which is, I believe, true for most of the other situations also. Yeah, so because we still don't know which is the future qubits, which could be the future qubits. I showed you like a list of different technologies: NV center, trapped ions, atoms. Everyone, whole world, everyone is doing different of this. There are groups who are doing different technologies. They are trying to test which one would work, and obviously after 10 years maybe one or two of these will succeed, and then that would proceed and go ahead, because you need to also scale the system. So in that case, there are some drawbacks. I won't say disadvantage. Yeah.
Yeah, so I believe you have got your answer, Rima. So someone has WhatsApped me that can you please ask this question? Okay, now very interesting
Okay.
case. So do a mechanical engineer undergraduate have any application in quantum computation field? This is the question.
Hmm. Hmm. Okay.
Super shy
Uh,
soul, yeah.
Mechanical engineers. I'm not exactly sure about what mechanical engineers really do. I mean, in detail. But of course, I mean, if you need a quantum computer, you would need big space, big buildings, and everything. So I think at a big picture, you'll always have some scope, because the quantum computer is such a field which it started in, as I showed, in 1981, and with many engineers and physicists and mathematicians, and even among engineers there were computer science for software, and interface all those things. There were electrical engineers for all those lines and wires and everything going down the fridge. There were electronics engineers and everything. But yeah, you can always use you can read about quantum computer and then find out where do you fit in. So it's like, it's like a community, a huge community, and you need to now figure out where do you fit in this community. So that's the idea. That's where the self-awareness comes from. um, in general, people can tell you that, okay, if you are a computer science engineer, then you can get into this. But again, you need to find out that what particularly you are interested in, and what computation is demanding, and how can I fit into it. But I would say that maybe yes, there be some of the scope opportunities for all of the engineers, even. Yeah.
Okay, so your reply is that research at your interest level has to be done so as to get into
Yes.
what exactly you want, right? Yeah, yeah.
True.
It is
True.
far too, yeah. So, okay, this is last question from my end. If any one of you want to ask any more questions, we are always welcoming you. Okay. So, what is the can you just compare the PhD life in India versus foreign? Because I believe you have been through many physics scholars in India as well. In either you have been through many physics scholars, and you may compare their life to yours. So, can you compare it?
Okay, that's an interesting question. First of all, I mean, I haven't lived the life of a PhD in India. So, but as you told Saurav, yes, I have been very close friends with some of PhD scholars in India. So from their experience, I can say that the main difference is that here I'm sure that I will finish my PhD in 4 years. But in India, I have seen many of my seniors still continuing their PhD in 6 years, 7 years, and 8 years. In worst case, even 9 years, and it's long. So the certainty is not there. And yeah, I think that is one of the, if you say the timeline, that is one of the thing which I see is different. And the other thing is, anyway, it all depends on, you know what kind of person you are. If you're a social person, then obviously different place has different kind of society. Yeah. Yeah, so there would be different lifestyle. Is obviously that's a different, that I think you even can guess that. So I don't want to speak on that, but the main difference could be, in the fact that it sometimes it takes longer in India to finish a PhD versus Europe. Yeah, that one thing I can tell you for sure.
Got it, got it. So your reply is that in India, your PhD may end up being a struggle, right?
Yes.
Okay,
I mean,
okay.
struggle, it's struggle everywhere, in the sense that you have to put effort into it. You have to put some time, effort, and everything into it. But time wise, it takes relatively longer in India than in Europe.
Got it, got it. So here I have a question from Aniket Sarkar. So its question is, in qubits, you said some alpha 00 beta 01 gamma 10 and delta 11. What is this?
Yeah.
So
So
technicality he is asking about. Yeah.
Yes, yes, yeah, I get it. So if you have, I'll just reduce this to 1 qubit. So this is for 2 qubits. So if you have 2 qubits, you have 4 states in classical. Let's say in 2 bits, you have 4 states: 00, 01, 10, 11. But in quantum, you have superposition of these states. Superposition means addition of these 4 states. And when you add them, then you have some factors. These are alpha, beta, gamma, delta. So they could be superposed in different degree, not equally. If they're equally superposed, then the alpha, beta, gamma, delta would have same values. And so for 2 qubit case, for 1 qubit case, let's say if you have 1 qubit, it could be either 0 or 1. And in qubits, it would be alpha 0 plus beta 1, right? And if they're maximally superposed, then it would be the alpha and beta would be 1 by root 2. So it's like the normalization constant. And in different degree of superposition, this alpha beta could have different value, and then you have different states accordingly. Yeah, this is the constants. Yes.
I believe you got your answer. So, yeah, are there any more questions? Are there any more questions? I believe no. So, first of all, let me give my ending speech. So, first of all, I would like to thank you, Dipankar sir, for being here. And it was really a really great experience being with you on this journey, on this short journey. But matter is, it was really an interesting one. Many have missed. They will be. I'll be definitely referring them to watch on YouTube. The live session is already being streamed on YouTube, and anyone anytime, be it you after 5 years, today, tomorrow, can anytime watch it and get the experience of these 1.5 hour or 1 hour what we had. So this was really a very nice session, nice interactive session to future demanding insights we have got, and this was really not possible if we have not got you over here, because this is something very unique kind of a skill or unique kind of domain that very few scholars have been working on like you. So it was really a matter of privilege for us, and matter of fortunate for us that we had you on over here. And we would really like to thank you like anything. And we are definitely looking you forward to have you next year take over session 2. So I believe you are also excited and had a good time with us. Thank you very much.
Yes, yes, Saurabh. Thank you so much for inviting me. I always enjoy talking about quantum computer, and also talking about careers and how can you move forward in your career. So it's not that difficult. So I hope, I wish all of you a great success in whatever you are doing on all fields of engineering. And big applause for all the organizers for organizing this tech fest. I know it could be a tough job at some point, and it's good that there are so many people listening. I'm really happy. And yes, thank you, and have a nice evening, I believe. Yeah. uh, yeah.
Okay, so now I am testing the. Okay, so Ankush, stop the streaming first and then reply me. हाँ
Okay,
streaming
good
खत्म हो
that
गया ना.
you are doing it and streaming also. That could help the others too. Nice.
Yeah, yeah,